Hello, general physics students. Yesterday in lab, we ran into some confusion regarding the term phi. A lot of you were worried that your phi values weren't the same, and so I wanted to create a quick video to explain what we mean by this parameter, the phase shift phi. So as a quick review, let's just recall the equations we were using. We were modeling harmonic motion where the position was given by the function a sine, let's get our n, omega t plus phi. Likewise, we had velocity as a function of time, which is equal to a omega sine omega t plus pi over 2 plus phi. And then finally, we had acceleration as a function of time is equal to a omega squared sine omega t plus pi plus phi. And so a lot of students were astutely noting that, oh, my omegas should be the same when the equation is generated. But a lot of you were worried that, whoa, these phis don't agree. In other words, you were noticing that phi of position was not equaling phi of velocity, which was not equaling phi of acceleration. And this caused a lot of consternation among some of us. I just noticed a quick error. There should not be an equal sign there, but we can't fix that now. That should be a as a function of time. Sorry for the confusion. So first, let's talk about what phase actually means. If we plot a traditional sine function like this, you'll notice that when time is equal to 0, the position is equal to 0. If we were to make some other function, let's just call it g of x, equal to, well, the same amplitude, and it will have the same omega value. But now let's add some phase. Let's do something like 1, sure. And so you'll notice here that now when time is equal to 0, the position does no longer equals 0, but equals what appears to be around 2.1. This is what we mean when waves are out of phase. When we add this phi factor, it shifts the function. And so first I want to address mathematically why you were getting different phi values. So let's move here and focus more on the mathematics. There we go. So Capstone is not smart enough to add this pi over 2 term. What Capstone was doing is it was taking these two terms and giving you a single term phi of v, which is equal to phi of x plus pi over 2. This is the value that Capstone was giving you. And so you should be getting different phi of v and a different phi of a, because Capstone automatically combines these two terms. That is why when you're doing the analysis, you should subtract pi over 2 from that phi of v, and you should get your phi of x back. By the same token, phi of a was made up of these two terms, phi of x plus pi. And so we should expect that these should not be the same value. So that's the mathematical explanation. And so in your analysis, if you're realizing that your phi values are different, that's okay. The important thing is that after you do the math, you should get your phi of x value back. Let's look at what that looks like graphically. So we've added pi over 2 to the phi of x. And so if I'm going to plot velocity here next to position. Now technically, if I want to be super accurate, the velocity should actually be equal to 3 times 2. And then let me just quickly say what this would look like. So it should really be 6 times sine of 2x. plus pi over 2. So that's what it should really look like, but for the sake of visualization, I think this is okay. What I want you to notice is that they are being 90 degrees out of phase. When one function is at 0, the other is at a maximum. What I mean by maximum is either positive or negative magnitude. So when the position is at its equilibrium point or 0 point, the velocity is maximized. By the same token, when velocity is equal to 0, this is when the pendulum has reached one of its two extremes. And so when they are 90 degrees out of phase, when one value is 0, the other value is maximized, either positive maximum or negative maximum, or you might think in terms of extremes. So this is when two things are 90 degrees out of phase. So position and velocity are 90 degrees out of phase. And so when one is at 0, the other is at its maximum value. Position and acceleration are actually 180 degrees out of phase. If you're not familiar with radians, pi over 2 is the same as 90, and pi is equal to 180. And so here we see that when the position is at its positive maximum, the acceleration is at its negative maximum. In every case, acceleration is opposing the motion. This is the whole idea of Hooke's law. There's one other relationship I want us to examine. I'm going to keep acceleration and then have velocity. So position and acceleration were 180 degrees out of phase. Velocity and acceleration were 90 degrees out of phase. And that makes sense because pi over 2 plus pi over 2 equals pi. And so what I want you to notice here is that when velocity is at 0, the acceleration is at its maximum. And when velocity is at a maximum, acceleration is 0. So again, this idea, when things are 90 degrees out of phase, when one value is at its maximum magnitude, the other is at 0. Whereas, let's again put acceleration in position, when things are 180 degrees out of phase, when one parameter is at its maximum positive value, the other parameter is at its negative maximum value. So now that we have a mathematical idea behind this, I want us to play with a brief simulation to kind of simulate why this is. So I'm using what's called PhET simulations. It's phet.colorado.edu. It's a series of simulations that help clarify physics concepts. And so I've toggled on the velocity vector. We're going to see how velocity and motion interact with each other. So remember, I said that these two were 90 degrees out of phase. So as one increases, the other should decrease. So let's get this moving. You will notice that once the pendulum reaches its equilibrium position or its 0 position, the velocity, let's plot velocity, when the pendulum is reached a 0 position, the velocity is largest. Let's get it running again. So we're just going to have it run a little bit for you to see what's going on. And just notice, every time it approaches that 0 point, the velocity vector is at its maximum value. By contrast, let's see what happens when the pendulum reaches one of its extremes of its swing. Now, position is at a maximum value, whereas velocity, the vector, is almost non-existent. So this is the idea of being 90 degrees out of phase, that when one parameter increases or reaches its maximum value, the other parameter is decreasing. Unfortunately, I wish I could show acceleration. It seems like they're showing a different type of acceleration than what you were measuring. The way I want you to think about it, though, is here at the bottom, when its velocity is maximum, it is no longer having positive acceleration. It's now going to actually start decelerating. Whereas here at the top, when velocity is equal to 0, now it has the full force of acceleration trying to pull it back. So again, when it reaches the bottom, it has reached its maximum swing. There is no more acceleration in that direction. It's going to start accelerating in the opposite direction. So I hope this brief simulation gave you an idea of how position, velocity, and acceleration are related. Position and velocity are 90 degrees out of phase, so that when one increases, the other decreases. Position and acceleration are 180 degrees out of phase, which implies that when one has reached a positive maximum, the other is at a negative maximum. I hope this clarifies some concepts. Please turn in your lab report by midnight tonight. If you have any questions, do not hesitate to contact me via email or try and track me down during my office hours. Have a good day.